Good morning, ladies and gentlemen. Welcome to the 2007 Shaw Prize Lecture. My name is Annie, a research postgraduate student in European Studies. I will be your master of ceremony for this morning's lecture. First of all, may I invite our Vice Chancellor, Professor Lapji Choi, to say a few words. Professor Choi, please.
Professor Goldright, members of the Goldright family, Dean, distinguished guests, ladies and gentlemen. It's really gave me great pleasure to welcome you to this University of Hong Kong. And it's really a privilege for us to host this Shaw Prize Lecture in Astronomy this year. And I'm delighted to welcome Professor Peter Goldright to the university. It is really an international award, as you know, that established by Sir Runman, and then it honors individuals for achieving breakthroughs in academic and scientific research or application, and whose work have had a positive and profound impact on society. I'm sure that you all know that this award actually put Hong Kong and high institutions in Hong Kong on the world stage. And of course, this is a scientific universe I'm talking about. So it is very much an honor that Professor Goldright, a distinguished expert in theoretical astrophysics and planetary sciences, will be lecturing us this morning, and he will be sharing his insight, expertise, and experience with us this morning. Among his significant contribution to the field of astrophysics, many of Professor Goldright's greatest contribution have been to our understanding of how planets form, migrate, and evolve. Dean will later on make a proper introduction of Professor Goldright's work. Now, I was at the award dinner last night. I heard Frank Xu saying that the past 50 years represent a golden age for astronomy. I think it's fair, because we always say that this century belongs to biology and medicine. Now, so no wonder in Professor Goldright's remark in his acceptance speech, he referred himself as an environmental scientist, of course, studying of a different kind. So I was particularly impressed by the way Professor Goldright wrote in the program book, and I think this is particularly fitting for the students in the audience. So with their permission, Professor Goldright, I can read a part of your writing here. It's a very small print, so I have to adjust. A quote: "I'm a general purpose astrophysics. My goal is to understand natural phenomena revealed by astronomical observations. When a discovery piques my interest, I try to find the physical mechanism that underlies it. Often I devise a simple model where I can analyze it to see if it captures critical aspects of the phenomenon. Typically, astronomical observations offer an incomplete picture, so this step involves inspired guesswork. After a while, if I don't succeed, which is the most frequent outcome, I'll go on to something else, while remaining vigilant to clues that new observations may offer. If I feel I have made significant progress, I report the results in a paper." I think that's all we do. Now, the idea of origin and change and development in particular is particularly relevant to Hong Kong U today. The university was founded in 1911 to provide a modern tertiary education for local students for the benefit of Hong Kong and China. Among almost a century on, the university has moved with changes that have affected our world, building on the strengths of its history to meet the needs of an internationalized knowledge-based economy. Now, we continue to move forward with this dedication to excellence, and we extend our mission of service to include the global community. Now, my congratulations to all those involved in the Shaw Prize Foundation on this very important and memorable occasion, and please join me again in welcoming Professor Goldright.
Thank you, Professor Choi. May I now invite our Dean of Science, Professor Sun Kwok, to say a few words and to tell us more about our speaker. Professor Kwok, please.
I'm very happy to see this room is totally filled. It's my great pleasure this morning to welcome Professor Peter Goldreich, the 2007 winner of the Shaw Prize in Astronomy. Professor Goldreich currently is a professor in the School of Natural Science of the Institute for Advanced Studies in Princeton. Before that, for 36 years, he was a professor of astronomy and planetary science at the California Institute of Technology. And he retired from that institution in 2003 and went over to Princeton in his present position. Before he joined Caltech, he was assistant professor at the University of California at Los Angeles in astronomy and astrophysics. That was in 1964 to 1966. Professor Goldreich was born in New York City, USA. He received his bachelor degree in engineering physics at Cornell University in 1960 and his PhD in physics in 1963. He's a member of the U.S. National Academy of Sciences. Professor Goldreich has made many significant contributions to modern theoretical astrophysics. Topics are really too many to completely list, but among which are pulsars, masers, oscillation of the sun, and planetary rings. And Professor Goldreich is not only an excellent researcher, he's also very committed and inspiring teacher. He has trained many students and postdoctoral fellows over the years, many of whom are now currently prominent astronomers working all over the world. Now, although I myself do not have the good fortune of having worked with Peter, but I still remember very fondly the time that we spent together in 1990 at the University of Colorado Institute for Joint Institute for Laboratory Astrophysics. I think both we were visiting fellows. And today, he is going to talk to us in a very exciting and I think relevant to many aspects of our life, a problem of the solar system, namely examples of chaos in the solar system. Professor Goldreich.
Thank you for those very nice words. Thank you, Vice Chancellor. Thank you, son. Oh, already an example of chaos in human behavior. This is a very difficult subject that I'm going to try to introduce you to, and nobody completely understands it, including me. So please don't give up if you find some of it confusing. Just try to get what you can out of it. I'm going to start very simply by showing you examples of chaos involving a simple pendulum that's shaken and then a double pendulum. I've brought a double pendulum with me, and then I'm going to go on and tell you about 3 examples in our solar system where chaos plays a significant role. And there, all I'll really be able to do is to show you where the pendulum is in the dynamics. I'll try to illustrate why a pendulum really shows up in these much more complicated systems, and I'll say a few words about why the pendulum is chaotic. And then after the lecture, I've brought a couple of pieces of meteorite. For those of you that have never touched anything that predates the formation of the Earth, you can touch the iron meteorite, but not the stony meteorite, because that's still a research object. And if you're careful, you can play with a pendulum, but it can break fingers, as you'll see. So you want to be careful with it. Okay, so So this is a sort of schematic of our solar system. Here an example of some of the objects that that we're going to be talking about. I want to try to get a pointer here so I can point to them. There we go. Okay, so we'll start off, as I said, with a simple pendulum. I'm going to introduce you to the types of motion that a pendulum can make. And then after that, we'll discuss slightly more complicated versions of a pendulum. So this is my simple pendulum here. It's a rod with a ball at the end of it. And everything I'm going to show you about the dynamics of the pendulum and also the other objects that we're going to discuss, all of this comes from integrating the Newton's equations of motion and then adjusting the solutions to be graphically displayed. So there's no poetic license here. It's all integrations of the equations of motion. So the first thing I'm going to show you is the types of motion that a pendulum can make. And the first one is called libration. So this is a type of motion that a single pendulum can make. It's a very simple periodic motion. It goes on and on forever. It's typically used by hypnotists to put clients under a spell, and we don't want to do this with an audience. So we'll shut this off fairly quickly and go on to the next example. So this is libration of a pendulum. A little bit more interesting than libration is circulation. When a pendulum is given a little bit more energy than it's needed to make it librate, it can circulate, and it can circulate either clockwise or counterclockwise. Oops. Uh-oh. Already in trouble. There we go. I made these movies. It was the first time I had computed since the mid-60s, mid-1960s. It was really almost killed me. Just putting the thumbtack into the rod there was a big effort for me. It took me half a day. So this is circulation. It also goes on and on forever. It's periodic motion. It's very boring. And so we'll shut it off and move on. Now the next type of motion that I'm going to show you is one that separates libration, the small amplitude motion, and circulation. And we can only approach that type of motion. This is motion on what's called the separatrix. And motion on the separatrix is the heart of chaos. So this is actually quite important. There we go. So here you see the pendulum just barely goes around once, and then it's hard to tell what's going to happen next. You have to wait to see. Now it turns out I know the answer because I made the movie. But you can see here that the pendulum is balancing very nearly on its point, and eventually it's going to decide to move one way or the other. And so now you can see that this motion is really a very large amplitude libration. The pendulum went back the same way that it came. It's on the libration side of circulation. But while the pendulum bob is pointing vertically upward, the pendulum is extremely sensitive to any sort of little perturbation, any little blowing of the wind, if there's wind around, even quantum mechanical fluctuations, if it's a small enough amplitude mass pendulum. And because of this, motion near a separatrix is really at the heart of chaos. And all the examples I'm going to show you, that's actually the case. All right, so now we're going to go on to the next most complicated version of pendulum. So far, we had a simple pendulum, just a rod, a ball, and a fixed pivot, tack fixed in space. Now we're going to discuss the next most complicated pendulum. This is called a parametric pendulum. Here we have still the same pendulum we had before, but now we're shaking the pivot point up and down. And the pivot point in this case is being shaken with an amplitude which is 1/20th the length of the rod, and at a frequency which is about 5 times higher than the natural oscillation frequency. And now I'm going to show you the sorts of motion you can get with a parametric pendulum. Sorry, these things take a little while to load because I haven't been able to figure out how to put these movies into the PowerPoint itself. Whoops. Oh dear. This isn't good. My son said that when this happens, I should say that sometimes chaos affects these performances as well. I may have to start this again to make sure that yeah, that's too bad. Let's see. Okay, so here I have a single pendulum, but it's being shaken at the pivot. And there are actually 2 pendula here, one behind the other. You can't really see the one behind at the moment because it's hidden in the one in the front. But initially, these 2 pendula were separated in angle by a millionth of a radian. This is the angular resolution of the Space Telescope. These pendula are moving at a speed characteristic of a pendulum that's 10 meters long. And if we watch this movie, you would never see the one that's behind the one in front separate from it, even if you waited for several hours. And we don't have several hours here. So this is an example of a parametric pendulum which is making a regular motion. And I'm going to show you a different version of a parametric pendulum in which the motion is not regular, but is chaotic. Oops. Wow. I'm having much luck here. I don't know why this is giving me so much trouble. Okay. This is very strange. Let's start again. Okay, so now I'm going to show you the same double pendulum, parametric pendulum. But with a larger amplitude initial excitation. Again, the two bobs, the two pendular bobs, have been separated by a millionth of a radian initially. Otherwise, the initial conditions were exactly the same. And we'll watch this now for about 20 or 30 seconds, and we'll see something really remarkable happen. See this, oh, there we're getting motion very close to separatrix motion. Again, pendulum was, first when it was going clockwise, and now it's going counterclockwise. Now the two pendula are separating. They're actually identical dynamically. I've just made a thinner representation for one than the other so I could line them up and you could see both. Now you see they're going in opposite directions. So this millionth of a radian in 20 seconds has become a full radian separation. Pendula now moving completely independently of one another. This is an example of chaos, an extreme sensitivity to initial conditions. This actually characterizes our lives. Very small inputs that we receive during the day can completely change how we feel about ourselves, what we go about doing, and so on. And it also characterizes many other systems, systems of weather, and so on. So this is the first and simplest example of chaos involving a pendulum, and actually an example that shows up over and over again in more complicated systems. Okay, so now I'm going to go on to a double pendulum. A double pendulum can make regular motion. Here's an example, I hope everybody can see, of a regular motion of a double pendulum. There's a little damping here from friction, not a lot. But you see nothing very spectacular here. So I won't bother to show you this in the movie, but now I'll show you an example of chaotic motion involving a double pendulum, which is much bigger than this one. Double pendulum, which was 10 meters long instead of order half a meter long. So here we're looking to see what happens to this millionth of a radian separation, actually just in the lower rod of this double pendulum over time. And look what happens. First, not much is happening, and now almost like an Olympic vaulter, you see the motion changing quite a bit. Energy is being conserved here, but when the lower bob is low down, the upper bob can really move. And look, just after 20 seconds, this millionth of a radian again has become a full radian. So this is another example now with 2 degree of freedom system, 2 angles determining the orientation of the pendulum, of how you go from regular motion to chaotic motion. And this is very nice because we can represent this with a little model here, like the one I brought. This isn't even a particularly good model that I brought to show you. But let me illustrate now. This is more dramatic than what you've seen in the movie because it's smaller and so it evolves faster. So you can see. Now, of course, it's damping because of friction. But even when you think it's dead, it sometimes surprises you. So you want to be a little careful. Now, of course, this is a purely mechanical system. There's nothing very complicated about it. But no computer can predict for the time that you watch this how it's going to behave. Not the best computer in the world. And in fact, the movie I showed you, if I told you what initial conditions I used, and I gave it to your most computer-able students, and I left out 1 digit in the 16th figure, they wouldn't be able to reproduce that movie for let's say 30 seconds or so. They would get a deviation which made the solution look completely different from the one that I showed you. So if you sometimes feel like your life is chaotic, this is why. Okay, so now the next part is a little bit more complicated still, because now I'm going to try to illustrate, also by way of movie, where a pendulum lies in complicated and more complicated dynamical systems. Still not the most complicated, but more complicated. So the first one I'm going to talk about is orbital resonance. I'm going to tell you something about orbital resonance. I'm going to show you what we mean by an exact 2-to-1 resonance. There are many asteroids that are in or near 2-to-1 resonance with Jupiter. Their orbital periods are very nearly half that of the orbital period of Jupiter, as both Jupiter and they go around the sun. There are many examples of orbital resonance in satellite systems of Jupiter, Saturn, and so on. And I'm going to show you with a movie what we mean by orbital resonance. So the first one is shown here. Every time I click on one of these movies, I get this sort of feeling in my stomach that, oh God, I don't know what's going to happen, but I hope it works. Okay, so here we have our asteroid running around. Here's Jupiter. Here's our asteroid. Our asteroid is in a smaller orbit, and it's moving around faster. Just Kepler's laws. Here's Jupiter. Okay, so the asteroid's gotten around the track once. This arrow is pointing towards the perihelion of the asteroid's orbit. That's the place where the asteroid is closest to the sun. This is the sun. Now the asteroid is catching up with Jupiter in longitude. And since this is an exact 2-to-1 resonance, the asteroid's going to catch Jupiter right here in its perihelion. This circle here just is the average orbital radius of the asteroid. And even this movie even activates the motion of the perihelion of the orbit. So here we have it going around again and again. So this is exact 2-to-1 resonance. Now resonances are very important in planetary rings, in Saturn's rings. There are gaps in resonances where there is no ring material. In the asteroid system, the density of asteroids near resonances is low. In satellite systems, the probability of having a second body at a resonance is high. All this is now understood, although it wasn't as recently as 50 years ago, or even 40 years ago. And it turns out all of this understanding involves chaos. So I'd like to at least show you that there's a pendulum in this system. And for that, I'm going to show you another movie. Now here I'm showing you this system strobed. So what I'm going to show you is a snapshot of the system we were just watching each time the asteroid and Jupiter in what we call conjunction, in which they're on the same line, same radial line pointing away from the sun. We're just going to strobe the system at that time. So here we see this is again all based on calculations. Here we see the asteroid, here we see Jupiter, and here is the direction towards the perihelion of the orbit of the asteroid at the time when the asteroid and Jupiter are in conjunction. And here I've chosen initial conditions for the asteroid motion So we're only close, but not exactly at this 2-to-1 resonance. And that then gives rise to this pendulum-like oscillation of the perihelion. Remember, we're just strobing this system. There have been 2 periods. Each strobe occurs after 2 orbital revolutions of the asteroid and 1 of Jupiter. So here's a pendulum. And this pendulum becomes chaotic in reality because the system is a little bit more complicated than the one I showed you. And the complication, the essential complication, is that Jupiter's orbit is eccentric, somewhat eccentric, unlike what I've shown you or calculated for you, where I've assumed Jupiter's orbit is circular. And that's enough to make this pendulum chaotic and also to clean the asteroids out of this 2-to-1 resonance. And this understanding, this discovery, is due to a student of mine who's now a professor at MIT. And he has the wonderful name of Jack Wisdom. And he made a career of understanding chaos in the solar system. He'll come up again a little while later. Okay, so that's 2-to-1 resonance. There are many other examples of chaos in the solar system. Only a few unfold fast enough so that human observation is frustrated by chaos. And the next one I'm going to show you is one I worked on with a former postdoc of mine, which unfolds very quickly, just in a matter of several years, and which was a surprise. And this involves 2 small satellites of Saturn. These are called Prometheus and Pandora. This is Saturn. This is the rings as seen by the Voyager spacecraft. Here are the 2 satellites. Their brightness has been enhanced and circles have been drawn around them so that you can see them. And what happened here is that these satellites were discovered in the early days of Voyager. These are actually the satellites that are confining a narrow ring of Saturn called the F ring. And orbits were fit to these satellites by the celestial mechanicians at the Jet Propulsion Lab. And then the satellites weren't seen again for about 15 years. They're very faint. They're next to the rings, which are very bright. And so they weren't looked at for very in a very precise way. But then the sun and the earth go through the ring plane of Saturn. The rings every 22 years, and the rings become much less bright. And when this happens, it's easy to see these small satellites. They were recovered in observations made with the Hubble Space Telescope. And they were found to be very far from where they had been predicted to be. In fact, they were found to be about 20 degrees away from where they had been predicted to be. And one of them was found to be 20 degrees farther forward from where it was predicted to be, and the other one was found to be 20 degrees farther back from where it was predicted to be, as illustrated here. These were the predictions here for where they would be in longitude, somewhere in this band, and this is where they were found to be. And this was interesting to me, and I had worked with Nicole previously. She had changed her name since. Typical American custom. She's French, but typical American way when she came to America, she changed her husband and her name, and it's now Rappaport. Anyway, we calculated in a simple model for the dynamics of these 2 satellites, and we found that they were chaotic. They were chaotic because they were perturbing each other. even though they're very small bodies, only about 30 or 40 kilometers in radius, they perturb each other's motions, and this accounts entirely for the chaos. And in fact, the chaos causes their orbits to be unpredictable on periods longer than about 3 years. Very short time. Okay. So we'll leave that now. And now I want to come back and talk about Mars. Mars is the next planet out from us. Mars has a rather low density atmosphere. Its pressure at the surface is only about 6/1000ths of the pressure at the Earth's surface. Mars' atmosphere is mainly carbon dioxide. And the atmosphere of Mars condenses in the winter in the north and the south poles, and dry ice, CO2 ice, falls out, and this causes the atmospheric pressure to change by about 30%. There's also a significant amount of water ice collected at the poles, enough to, if it were melted, could be melted and distributed across the planet, would give seas, global seas of 100 meters or so depth. So the evolution of volatiles and the climate on Mars is a very interesting subject. Now the seasons on Mars, just like the seasons on the Earth, are controlled by what we call the obliquity of the spin axis of the planet. This is the angle that the spin axis or rotation axis of the planet makes to the normal to the planet's orbit. For the Earth, this angle is around 23 degrees. For Mars, it's a little bit bigger currently, but only a touch bigger. In the case of the Earth, small variations in the obliquity of the Earth cause changes in the intensity of the seasons. But as far as we can predict, these variations are very small. The Earth is protected from large obliquity variations by our moon. This is a modern understanding, actually. Now, in the 1970s, I had a student named Bill Ward, and he investigated the dynamics. Oh, before I get on to Bill, this shows an example of the waxing and waning of the seasonal polar cap, the northern pole of Mars. These are photographs taken from the Space Telescope at different parts of the season. Most of the change here that you're seeing doesn't involve the water ice, but involves CO2 ice, which freezes out of the atmosphere in the northern winter and then is sublimated back into the atmosphere and freezes out of the atmosphere in the South Pole during the southern summer. This leads to variations of about 30% in the pressure of the Martian CO2 atmosphere. Okay, now there's a lot of evidence on the surface of Mars for channels that have been cut by water flow. Here are some examples of them, here and here. There's no doubt that water flowed either on or just below the surface of Mars in the past, probably in the quite distant past. And at present, liquid water is not stable on the surface of Mars. And the question is, or one question is, what was Mars doing a long time ago? Was Mars subject to very large climate variations? And what my student Bill Ward found was that the obliquity of Mars, the angle between its spin axis and the normal to its orbit, could undergo great variations over timescales as short as several million years. For the Earth, as I've mentioned, these variations are very small. We now know as a consequence of the Earth having a large moon. But Mars only has 2 puny moons, and it has these very large variations. Well, about 10 or 15 years after Ward did his work, this work was looked at again by two groups, one led by Jacques Lascar, it's referenced here, and the other one by my former student Jack Wisdom. And they found that these variations, which Ward had calculated in a simple model, when calculated in a more accurate model, were chaotic. And so the obliquity variations of Mars are chaotic. Here shows predictions going back in time of these chaotic variations. Now this is variation in the obliquity shown here. You see the obliquity going from below 17 degrees or down to around 15 degrees up to above 45 degrees over a period of 10 million years. Now you can't trust these calculations because they're just a representation of the sort of variation you can get from a chaotic system. But without knowing every detail, you can't trust these calculations even back for a fraction of a million years. But these are the sort of variations, and they lead to large variations in the amount of light that falls on the poles of Mars, and presumably in its climate. And we hope someday, soon actually, because we have a spacecraft going here, to have a spacecraft go and study these layers in the ice cap, northern ice cap of Mars, which rise 2.5 kilometers above the surrounding plains, and to see if they contain some record of climate variation on Mars. So this is something that's going to happen very soon, within the next couple of years. So this is another example of chaos, and now I'd like to illustrate where the chaos comes from. Okay, so this is my planet, or my planet model, or at least the picture object that I was able to attach to the calculations I did for you. And there are three axes here. This is somewhat complicated. There's one axis, which is the spin axis of the planet. That's this green one. There's a second axis, which is the red one, which is the normal to the orbit of the planet. And then there's a third axis, which is the normal to what we call the invariable plane of the solar system. It's a plane which is fixed in inertial space. And because there's more than one planet going around the sun, and the planets perturb each other, the orbit normal actually wobbles a bit with respect to the normal to the invariable plane. And I want to show you now that there's a pendulum in this dynamics. So we're going to go through 3 movies and see if we can at least get some idea how this works. So the first movie just shows precession. Okay, so here I've just shown you the invariable normal, the black, and the spin axis, the green, and I'm showing you a simple precession, just like the precession of a top, of the spin axis around the invariable plane. As far as this is concerned, the orbit normal and the invariable plane normal are the same. The orbit is in the invariable plane. So this is a periodic motion. It just go on forever. There's no very interesting dynamics in this once you understand it anyway. Okay, the next one, I'm going to show you a resonance state, sometimes called the Cassini state, in which both the orbit and the spin axis are precessing. So here you see the orbit precessing around the invariable plane, the orbit normal, and here you see the spin axis precessing around it. But they're precessing in such a way that all 3 axes are in the same plane. You have 3 lines in the same plane. This is a resonance state known as a Cassini state after Mr. Cassini, who discovered many astronomical things by looking through his telescope. Okay, so now I want to show you where a pendulum is present in this system. In order to do that, I'm going to strobe this system in the next movie. This is a gigantic movie, so it takes a while to load. All right. So what I've done now is I've set up my initial state. So we're not exactly in a Cassini state. We're close to it. And you see now, and I've strobed things so that I've taken a snapshot every time the orbit normal is in the same orientation with respect to the invariable plane. And I've looked at what the spin axis looks like. Now you're seeing the spin axis nodding up and down. This is a two-dimensional pendulum motion. And this is the motion that becomes chaotic. The reason it becomes chaotic in nature is that the angle between the orbit normal and the invariable plane normal actually change with time because there are several planets perturbing the orbit of Mars. And this then makes this pendulum motion chaotic. And it's a remarkable thing that only a half a degree variation in the angle between the red axis and the black axis can make the variation in the angle between the green axis and the black axis vary between about 10 degrees and 60 degrees. Fortunately for us, this doesn't happen on Earth. Although maybe we would have evolved quicker into more interesting beings if it had. All these discoveries were made sort of accidentally by people just poking around and asking questions. And it hadn't been anticipated that there would be such interesting dynamics. Okay, now I'd like to come to the last of my three easy pieces. This one I'll go through fairly quickly, and then I'll show you these examples. The Earth is bombarded by meteorites. Meteorites, and also to a lesser degree comets, produce big impacts on Earth, probably responsible for mass extinctions, and although not very frequently, fortunately. And meteorites come in two types. There are two types of meteorites. There are stony meteorites, the most common class of which are called chondrites. And this is an example of a chondrite. Chondrites are mainly rocks, but they have some features that we don't see in any terrestrial rocks. First, they tend to be about 25% iron, and a significant fraction of the iron is elemental iron rather than being oxidized. All ore deposits on the Earth, the iron is always oxidized. It's the iron oxide that gives color to many rocks, gives the reddish colors, and even bright red colors. And the second thing that's even more remarkable about chondrites is that most of their bulk is made up of little spherical objects, very nearly spherical objects of about millimeter size called chondrules. Chondrules, when they were discovered long ago by Sorbet, were called droplets of fiery rain. And these little white specks here are chondrules. And we still don't understand how these chondrules were made, why they're so common, why they're always millimeter size, and even why they're spherical. Although basically the reason they're spherical is because of surface tension. The same reason why small raindrops are spherical. Okay, and chondrites, even though they're very, very common among falls of meteorites on Earth, since they're not easy to distinguish from ordinary rocks, are about half the time found just because somebody sees them fall and then goes over and picks them up. The other half, somebody really notices that they're an odd type of rock. Nowadays, a lot of chondrites are found in Antarctica because there aren't any rocks on the ice sheets of Antarctica except things that fall from space. So this is now a way we get lots more chondrites. The other type of meteorite are iron meteorites, and this is an example here. And iron meteorites are completely unlike anything on Earth. They're typically 25% nickel, the rest iron. They're not oxidized. They're all elemental. They're very, very tough. They don't look like anything on Earth, and they last for a very, very long time once they fall on Earth. This is an iron sulfide inclusion in an iron meteorite. I brought an example which is very much like this. This is a slice through something that was more like a potato, and this is now a slice through it. This is also a slice through something which would be more three-dimensional. And I brought a little piece of one of these. And you can look, these, almost all of meteorites were formed within a few million years at the earliest time in the solar system. So we believe that the ages of solidification of meteorites give us the age of the Earth, the age of the solar system. It's about 4.56 billion years old. Oh, I don't know how that happened. This is sort of spontaneous. So. It may be that the wireless is somehow... but anyway, I want to just leave you with one final example of chaos. And this has to do with cosmic ray exposure ages. One of the great mysteries when I started out working in astronomy, one of the great mysteries in solar system dynamics was how the meteorites got to Earth. When meteorites, rock-sized objects, are broken off bigger objects like asteroids, a clock is started. And this clock counts the number of cosmic rays, number of high-energy galactic cosmic rays that strike this rock and penetrate. These cosmic rays can penetrate about 1 meter of rock. We're protected from them by our atmosphere, but these fragments from an asteroid aren't. And these cosmic rays then enter the fragments knocked off the asteroid, and they change the composition in small ways, the composition of the meteorite. They do that by breaking up nuclei, by spallation, the breaking up of nuclei. They create nuclei that are very uncommon in nature, but which can be produced by the bombardment, by the breaking up of common elements. And so when the meteorite falls on Earth, it has a record of how long it took from when it was broken off a big asteroid to when it got to Earth. It has even a better record. It has a record of how long it's been on Earth, because once it gets on Earth, some of these spallation products, which are unstable, decay. And their abundance can be compared with the abundance of the stable spallation products. We can not only say how long the journey took to get from the asteroid belt to Earth, but also how long the rock had to wait for somebody to pick it up. And it turns out that these timescales are very short. They're measured typically in just a few million years. And nobody could understand how these rocks got so quickly from the asteroid belt to the Earth after they were broken off meteorites. And this problem was solved by my student Jack Wisdom in the early 80s. And it's related to an independent puzzle, which was that the number of asteroids seen near resonances with Jupiter, where the asteroid orbital period was some fraction of the orbital period of Jupiter. So here we see 2 to 1, 7 to 3, so it would be 3/7 the orbital period of Jupiter. Here 2/5, 1/3 there were missing asteroids compared to the surrounding periods. Now, what wisdom figured out using a clever numerical technique which enhanced the speed of computations was that these gaps were due to the fact that objects placed in these near resonances would have chaotic orbits. The orbital eccentricities would be built up to large values. And then the objects would cross the orbits of planets like Jupiter, Mars, the Earth. They'd even plunge into the sun. And therefore, they were removed from the asteroid belt. And the understanding of how these meteorites then get rapidly to Earth is that there's some asteroid that's close to one of these orbits, not in it, not in one of these gaps, but close to it. It gets hit by some smaller object, some chunks come off. They have a slightly different orbit than the parent asteroid. They find themselves in one of these gaps where their orbits are chaotic. The orbits build up large eccentricities very quickly. They cross the orbits of Mars and the Earth. And if we're lucky, at least if they're not too big, if we're lucky, they come down and strike the Earth, and somebody finds them and gives them to somebody who can analyze them and learn about their history. And so we now know that the depletion of these resonances takes place in just a few million years. So this problem of transport is now considered solved. Okay, so I guess that's the end of what I want to say. If you'd like to come up and play with the pendulum, make sure nobody else is in range, and also be very, very careful with your hands. It's probably better here if you break a finger than in the States, because the insurance is probably better. And then there are two meteorites. I brought a piece of iron. This iron is a no name. No name means that we don't really know where it was recovered. We don't know much about it. So it's really not a scientific object anymore of interest. But it is 4.6 billion years old. So you're welcome to touch it. So you can say you've touched something that's older than anything on Earth. Also, you'll notice there are little, if you rotate it, you'll notice there are little patterns that you can see here. Here. These little needle-like patterns. These involve the iron separates into phases that are more and less nickel-rich. And from the sizes of these little lines here, you can tell that this thing cooled very, very slowly, just degrees per million years, from, let's say, 2,000 degree where it was completely melted. And therefore, it was at one time the core. This was in the core of some fairly big body, like a large asteroid. And then there's this inclusion, this iron sulfide inclusion. That's a little fragile. Please don't push it out. But you're quite welcome to touch it. It's probably not worth more than several $1,000s, even in today's inflated market. More than my airplane ticket, but less than my prize. Okay, now, this other one, I brought a piece of chondrite. I used to bring a big piece of chondrite, sort of like this. But the last time I went down to our meteorite collection, I looked up, there's a market for these, and I looked up the value of the piece that I was about to bring, and I found out that it was comparable to the value of my prize. And I decided I didn't want to bring it in the airplane with me. These things always cause a problem when you bring them through the security, and sometimes the security wants to touch them. And if they're named asteroids, which are still objects of scientific study, we don't want them to be touched. So this, I brought two little fragments, but you can see the chondrules. I have a magnifying glass, and you just keep it in a little jar here, and everything will be fine. Okay? Okay, I hope I didn't intimidate you with all the stuff. Remember, nobody, including the lecturer, understands all of it. So, thank you.
Take some questions? Professor Goldwright kindly agrees to take some questions.
Oh, I'd like to have questions.
Yes.
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 Yeah. Professor Goldwright, since you worked a little bit on what's going on Mars, and now we know that temperatures on Earth are rising for 300, 400 years. Now, 50 years, it is accelerating. We are trying to figure out what is behind it. Now, the Hubble Space Telescope spotted on Mars that there is also some kind of rising temperature effect going on. Is there a possibility that the temperature rising machine, which is doing that on Mars, is the same, which is at least partly in the picture as far as what's going on Earth?
Well, actually, I don't know that there's good evidence that the temperature is rising on Mars. If you want to know why the temperature is rising on the Earth, just feel the air conditioning in this room and look at the traffic. That's probably the main reason, at least for the accelerated rising of temperature on the Earth. And then look, for those of you that, well, I'm not quite sure of the relation with mainland, but just look at all the coal plants that are being built in the mainland, and look at my country, which wastes power in an unbelievable way. And that's probably why temperature is rising fast. That's not to say that temperature doesn't rise a lot on the Earth and fall on the Earth naturally, but it's a question of rate. And at present, the temperature is really going up at a very fast rate.
The gentleman in the front here.
Maybe I don't need a mic. Can you hear me?
Yeah.
I can hear you, but you want to, I'll repeat your question.
Professor, you said that the lack of variation of Earth was due to the moon.
Right.
Now, that sounded extremely fortuitous and even religious, but it certainly did not sound chaotic. Can you say a few more words on that? How did that happen?
Oh, well, okay. Yeah, the way that, the reason that Mars's obliquity is varying is because the rate at which its orbit is precessing, the rate at which its spin axis is precessing is very close to the rate at which its orbit plane is precessing due to the other planets. In the case of the Earth, the orbit plane of the Earth is precessing about the same rate as Mars' orbit plane is precessing due to the action of the other planets. But because we have this big moon, and the moon is fairly close, 60 Earth radii away, but that in a sense is close. The Earth's spin axis is precessing much more quickly than Mars is, and much more quickly than its orbit is. So there are two very different frequencies involved. There's the sort of 26,000 years the axis of the Earth's spin precesses, and hundreds of thousands of years that the orbit plane precession takes place. In Mars, the spin axis, because there isn't this big moon, is precessing more slowly and at nearly the same rate as the orbit. That's the difference. So the moon, by making the Earth's spin axis precess rapidly, pushes the rate of precession to a much higher value than the precession of the orbit, and there isn't much coupling. And that's what saves us from big climate variations due to obliquity variation, which otherwise we would have.
But the orbital precession of the Earth is believed to lead to glacier periods and so on.
Well, there are small variations. Okay, the Earth's climate certainly varies naturally. And there are small variations in the obliquity of the Earth and the orbital eccentricity of the Earth and so on. And they probably do have some effect on climate variation. But these variations are tiny compared to the variations that Mars obliquity suffers. So we might expect that Mars has much bigger variations in climate. We don't know. We will, but we don't. I mean, this is something we really will know about. I mean, there are different timescales for increase in knowledge. It's going to be probably a long time before we find other civilizations. But it's not going to be very long before we know whether the climate of Mars changed on 10 million year timescales. That'll be a decade or so. We'll know.
Yes. Please.
I would like to ask, how can you predict the age of those meteorites?
Oh, well, you don't predict them, you measure them. Well, or you make measurements from which you deduce them. Yeah, the question was, how do we know the ages of meteorites? How do we know that they all are basically the same age? Well, the age we're talking about is the solidification age. And what happens when a rock, for example, or an iron meteorite solidifies is that during the solidification, different phases separate out. And some phases have more of one type of element, other phases have more of another type of element. And some of these elements are radioactive, they decay. In the case of the first dating of the age of the solar system, the important elements were the uranium element, uranium and thorium, uranium-235, 238, and thorium. So these elements decay into daughter products. And you can look and untangle from the different phases in the rock how much uranium was initially present, how much of the daughter products were originally present, and then you, from that, have a clock which you can work out how long it took from the time that the rock solidified into these different phases until it was brought into the laboratory and analyzed. That's where the ages come from. They come from radioactive decay. But there are many different schemes of radioactive decay, and you can get very good concordance of the ages from different schemes. So there's uranium-lead, there's rubidium-strontium, there's potassium-argon. And the ages are very solid. And the variations in the age, for example, we know that the chondrules in these chondrites, all of them formed within a few million years, just a few million years. And the Earth is 4.6, roughly 4.6 billion years old. So it was an instant in which these all formed.
Yes.
Professor Gurrai, about the Kirkwood gap diagram, we see asteroid depletion occurs for certain ratios of orbit period, but why not all integers ratio? Why is that ratio so special?
Well, the biggest dynamical effects, I can only give this in a crude sort of way, but it's true that every irrational number can be approximated by a ratio of integers. But it turns out that dynamically, the difference in the integer in the numerator of the rational number and the denominator of the rational number is important. So a 2-to-1 resonance, or a 3-to-2 resonance, or a 4-to-3, there that difference is 1. And that 1 means that in the dynamics, only a single power of the eccentricity of the orbit is involved. And the eccentricities tend to be pretty small. If you go to a 3-to-1 resonance, then there are 2 powers. 3 minus 1 is 2. 2 powers the eccentricity, so the effects are weaker. 5-to-2, it's already 3. 7-to-3, it would be 4. So So it's the low order resonances, and the order being the difference between the numerator integer and the denominator integer, which are really dynamically the most important. And we see that. We see that in asteroid system, we see it in satellite systems, and we see it also in the calculations that can be made now with computers of long-term behavior of the solar system. So we understand that pretty well.
Other questions?
You made the statement that currently the water state on Mars isn't stable,
Right.
and then you showed that great plot with huge variability that goes up and down.
Right.
So from your calculations, can you say have there been times when water is stable, and how frequently does that happen, and what kind of typical time scale do they last?
That's a big unanswered question. We can say how the amount of absorbed solar or incident solar radiation at the polar regions varies with obliquity. That's calculable, very easily calculable. But then the consequence of that is much harder. It's clear that there's a certain store at present of CO2 in the southern polar ice cap. And so if there was a lot more sunlight falling on that during the southern summer, the atmosphere would become denser. How much denser, we're not sure. If it becomes dense enough, then there's a chance there would be enough of a greenhouse, even though CO2 is a pretty lousy greenhouse gas as a linear molecule. There's a chance that the temperatures could become high enough and the pressures could become high enough at the surface so the liquid water would be stable. But that's a much harder calculation because we don't know the amount of CO2 or the increase that would be promoted by a change in obliquity, because we don't know how much CO2 is really available to be radiated by the sun. If there was a tremendous store of CO2, if there were big blocks of CO2, then we could answer that question. At present, the atmosphere is in vapor pressure equilibrium. In other words, the pressure in the atmosphere is determined by the temperature. But if the temperature went up a fair bit, that might no longer be true, because the CO2 that would be needed to get the vapor pressure up there might not be available. It may be there in the planet, but it might be buried in the soil. So we can't answer that. And and the other thing is that our understanding of stellar evolution, which is also pretty good, tells us that the sun was fainter in the past. And therefore, the fact that it looks like there was water running around in fair quantities a long time ago is a bit hard to understand.
Dr. Chen.
What caused the increase in the asteroid collisions about 600 million years ago? And also, you think that has anything to do with the sudden increase in diversity of life on Earth?
Oh, there wasn't any great increase. I mean, there were the asteroid belt is a remnant belt. It's grinding down. Collisions cause big asteroids to break. Asteroids aren't growing now. They're just breaking each other up. And so as the system is colliding and breaking itself up, collisions are becoming less common. But I don't think there's any evidence that there was a really unusual period. 600 million years isn't that far back. 600 million years is a long way back for Earth biology. But it's not a long way back for the asteroid belt. So there were a lot more collisions, and we know that because actually when there are collisions, they cause melting and they reset these clocks, these radioactive clocks. And so when we look at asteroids, we do see evidence of collisions. and the resetting of clocks. And we know that most of those collisions occurred a long, long time ago, billions of years ago, not hundreds of millions of years ago. But the asteroid belt is getting quieter. How much quieter? We don't know very well.
Professor, my question is related to satellites and the rain system. Suppose the satellites are moving in a chaotic motion, so will the particles within the rain also follow this motion to move in a chaotic way? If so, why don't we see a chaotic rain instead of a round rain system?
Well, that's an interesting question, actually. Well, the reason is that the particles in rings are undergoing collisions with each other, very frequent collisions with each other, gentle but frequent collisions. So a typical particle in Saturn's rings is having a gentle collision with its neighbors every few hours. And this prevents the buildup of large variations away from circular motion of their motions. They behave more like a fluid, which is forced, particles are forced to move more or less regularly with respect to their neighbors. And in this case, this is a fluid under the influence of an enormous central gravitational force from Saturn. So that's why. It's because of collisions. And collisions are very, very gentle. The ring particles are moving 20 kilometers a second around Saturn. Saturn's about 10 times the radius of the Earth. And they're going around Saturn in half a day. So they're going a lot faster than our airplanes go, 20 to 50 times faster than our airplanes go. But the collisions between them are only at this sort of speed. And it's very gentle, but they're enough to prevent the buildup of these very irregular orbits.
Okay, since we are running out of time, if you have further questions, maybe you can approach Professor Goldreich after the lecture. At this time, I want to thank you again for your great
So the question and answer session has come to an end here. Thank you, Professor Kwok, for being the facilitator of the session. Please take a seat. And thank you very much, Professor Goldreich. To express our gratitude, may I invite our Vice Chancellor, Professor Lapchi Choi, to present a souvenir to Professor Goldreich. Professor Choi, please.
Should I stay here? Okay.
May I also invite Professor Sun Kwok, Dean of Science, to join Professor Goldreich and the Vice Chancellor on stage for a photo.
Okay, hold this. Susan, do you want to come up? You want to come up? It's okay. It's not so serious. You know?
Would Mrs. Goldreich and Mr. Goldreich would like to come to the stage?
Thanks, very good talk. You finally seem relaxed.
Huh?
You finally seem relaxed.
Well, I was a little nervous about it. I don't know.
Thank you very much. And this has brought us to the end of the lecture today. Thank you very much for joining us this morning.
Yeah.